So now we come to the point where we actually have to do some stuff, so it's some math. We'll slowly. So we'll recall on my popular demand. I'll start with recalling the definition of Nakajima varieties, which is representation something like this. And what this is you take a cotangent. It's a cotangent space to a linear subspace. So it's where this rep is a linear representation of a group. It's a product of GL EI. So both V and W are vectors. And then you perform what's called the algebraic symplectic reduction of this. Means this is denoted something like, so I believe if I write an alphabet line, then nobody will confuse it with the GIT quotient. So what this thing is, so first what's representation? Representation is, so since we're taking some linear representation on this dual, then I can, instead of, so this is GL of some, let's say, some vector space EI. And so what's allowed here is so many copies, some number of copies of so many of these EIs, some number of them. It's actually convenient to arrange these multiplicity spaces so that there's some multiplicity space which we'll call WI. We'll write home from WI to VI. And so this is the defining representation of this group, and this is just multiplicity space. And then you take so many, so this you take some number of copies of defining representation. You could have also taken the dual to the defining representation, but since we're taking T star here anyway, so then in T star you're going to get the dual space, will be the homes the other way, so you get the dual defining. And then some number of homes, again, some number of these homes. Some number of homes from VI to VJ. And this is now the multiplicity I just write outside. Why are you taking this representation and not others? Is because this way you can show that this way when you take the quotient, there'll be no semi-stable issues, no finite stabilizer, so the GIT quotient will be smooth, so algebraic right. And so what's this multiple line mean? So in this change of multiple line, so first you write, so this is on, we have a moment map, so this is from T star to representation, there's a moment map called, goes to the dual of the Lie algebra, so this is maybe I'll call this product, call it GE. So this goes to the Lie algebra GE dual. And so what this map is if I take, so here is a vector in Q and a covector P, and the value of the moment map, so if I take the moment map of this and evaluate it on some Lie algebra on the side, like psi is an element of the Lie algebra, then what I get is P, the value of P on the tangent vector so this element acts on Q, since this is a representation, acts on Q gives you a vector, so the value of covector on this is this. And so this multiple line thing means, in a second, so this multiple line thing, I think 4 is enough. So This means there's a choice of a character theta. And so what this is, you first take mu inverse of 0, and that just means the geometric meaning of this is this: my covectors vanish on the tangent to orbit. So this means choose covectors. Perpendicular to orbits. Now I'm almost trying to construct the T star tutti quotient. But this is, yeah, I first impose this, and then I take the ordinary GIT quotient in this theta by my GV, and this is GIT quotient. With respect to the character, well, the character is this, it's just a product of the determinants of each component GBI and G of the determinants characters GLI, this is what So if there are stable points, if there are G stable points in the representation, then the cotangent bundle to that would be sitting as an open set in this when you first take the moment map and then you take the quotient. So right, and like I said, the choice of this in principle you can apply to any representation, but then you're right, and you'll get into all possible issues. I mean, all well-known issues in JET. And so if you choose this particular representation, then this particular sort of representation, then in fact this quotient, when non-empty, is a smooth, symplectic algebraic variety. And so this data of this multiplicity spaces. So what's the data here? The data of this Nakajima variety, this multiplicity space, are recorded by a quiver. Quiver is a bunch of arrows, and so if you have two nodes of a quiver, corresponding to some number I and j, and then what you put next to it, you put maybe vi next to this, and vj next to that, and you draw the dimension of this multiplicity space arrows from one to the other. And then to remember what were the multiplicity of defining representation, it's convenient to add a little pendant to every vertex of this quiver. And so what this moment map is concretely is that if I have my space in Vi here, Vj there, then the vector in my space would be something like a mat here, X, maybe I'll write it Q since I and the covector of the dual thing would be a map the other way, it would be P. And this psi, so if psi, if my psi I, this is in GL I, and similarly psi j is here, then psi on this action under psi, this goes, you post-compose with psi j, so psi j q minus q psi I, j I. And so now if we pair it with if we pair it with a covector, that means my moment map of PQ, the valid side, is trace of psi I PQ minus PQ. Traces of delta. Psi, yeah, that's right. Psi j q p minus pq psi I. And so you see that here, this moment map, what it does, it takes this pair, in this space it goes to p, to qp, and here it goes to minus pq. And so then the example we started considering last time is that when I take this data, I take my quiver here with dimension n and my framing space. This is called framing. So my framing space is one dimensional, I take one bit here. So then the equations I'm getting is that, so if I call this data, well maybe, and I'll call it x, and then the covector will call y, and this arrow I call A, and the blue arrow I call B, then the moment map equation becomes, so by this rule corresponding to x and y, get the commutator xy plus ab equals 0. And then so then the stability condition, if I choose, so in this case I get 1 theta. So I get this theta, which I'll choose to be positive, for example. Then the stability condition will apply that b is 0, and then A, my space V, V is generated, V equals, we apply to the numbers x and y to the A goes from one-dimensional space, it's just a vector. And so if you apply to y, that the whole thing spans. And so you recognize that this is nothing but so you pair the equation here to one base 0, then this thing goes away. And so what you see is a pair of commuting matrices plus a vector that generates the space, n-dimensional space under the direction of x and y. And so if you had to take and so what this is therefore this is the same. This space is Nakajima space. It's the same as the vector scheme. And the map is just this is spanned by ideal, ideals in x and y. Let's put and the map is just the kernel of this map from polynomials to V is my ideal. So then, in every subject involving classification of somehow, in every subject involving a word quiver has some classification, and the quivers got somehow quivers come in 3 types. There's the tame ones. Those are the AD quivers. And the corresponding Nakajima variety behaves like, so these are the right Nakajima varieties are, in here, for example, you can find cotangents to GLN what parabolic, and on general, so this, just in general think this behave like cotangent to homogeneous varieties. This is then there's affine, so the same affine A, U, and E, and these are the moduli shaped on the corresponding surfaces, AD surfaces. And this is why I would love to know their quantum cohomology, which we do, but somehow this is why, because a curve in the space is a shape on a threefold, and so this is enumerative geometry of curves in this spaces are the enumerative geometry of shapes on threefold. And then there's the others, I don't know, wild or something other, none of the above. And those are very interesting varieties, but they are awaiting. So in many aspects, they behave just as well as this varieties, but then we somehow we fair to say they are waiting to them. Better genetic interpretation. And so here this corresponds to this quiver is A0 hat, and this corresponding K surface is just C2, and so this is the example. Now, so now what was our, so I recall that the envelopes are maps from equivariant cohomology of a fixed locus or something like this was a symplectic, this was algebraic symplectic variety. And this was a torus acting preserving symplectic form. Form, and this goes to space. And so now what is acting on the Nakajima variety preserving the symplectic form? Well, a lot of things. Well, I just erased what's acting, so this maybe keep in mind. Well, so what does it act on? So what's an automorphism of Nakajima variety? So on now we would have an action of the following very big group. So first of all, so there's an action of a certain multiplicity group, which, well, I'll write C star, which does not preserve the symplectic form. The scales. So since cotangent space, you can scale the cotangent direction, and this scales cotangent direction. Scales connected. This is important. But does it exist? But it's not the one which is going to use here. So then of course you can act. There were all these multiplicity spaces. So you get by GL product of GL WI, and you get the product of GL this EIJ. the difference between this and this, so this is so to speak, this is referred to, this people call this actually change of framing, and this is called this action on edges. My quiver. And the difference between this and that is that this, on the arrows in my quiver, this acts trivially on arrows, and this acts non-trivially. And so, how does it manifest itself? Is that, well, a point in Nakajima variety is something, it's a bunch of matrices, which you can also say that this is representation of a quiver. Representation of a quiver is just assignment of a matrix to every arrow. And then if you have a torus action, then a torus fixed representation of a quiver is a graded representation of a quiver. So torus fixed representation of a quiver, I'll write this down, torus fixed representation of a quiver. Is a graded. And the difference between the framing action and action on edges is that in this situation, the arrows have degree 0, and they have non-zero degree here. And so the result of this, if I take the torus here, so maybe I'll write the result. We're not going to. It's a very useful thing to consider, but we just don't have time to do it. So if I take a stop torus here and look at its fixed point, then this would correspond to representations of a cover, really covered in the sense of topological spaces of my original group. Because if you think about it, become all this. We're not going to do it. Well, because today we won't focus on this one. This will be fixed points here, would be a representation of the same group. Here. If I choose my torus here, then fixed point. Will be the representation. Well, of disjoint union of the same group. In some sense, it's still a cover, but in this case, it's trivial, and this is not true. So what's the thing that's going on? There's nothing mysterious going on. It's something elementary. So suppose I choose, for example, choose the C star, we call A, which is a positive group that goes to the product of G of Wi's. And so how does it go? It's an element Z here will go to a matrix which has Wi prime eigenvalues equal to Z and Wi double prime eigenvalues equal to 1. Of course, Wi prime plus Wi double prime equals Wi. Then it's a great representation. That for every space of my representation, I have to decide, I have to split it into something of weight Z and something of weight 1. And the maps just go inside, so between things of weight Z and things of weight 1. So this. If I take W, this case, well, it's just going to be so already fixed decomposition of doubles, and we'll take a disjoint, we'll get a disjoint union over all ways to decompose V. It just says that every space VI, so this is corresponds to every space VI being split as disjoint is direct sum. This is just by direct sums embedded into my representation. Well, for example, if I choose that same, if I take the same quiver, but then replace this one by, I don't know, by R, and the corresponding moduli space, and this is the following data. This is generalizing what I've explained here, but and so this is the following given by the following data. We take this is the moduli space of torsion Cauchy's. P2 together of rank R together and second Chern class equal to n together with trivialization. The trivialization of f restricted to a line, which people usually choose to be a line the complement of C2 inside P2. This is trivialized. So this is trivial. And my GLW here, or GLR, here acts. So this is acts on this framing space. So this is I call frame sheet, and this GLR acts here by just automorphism, so on the trivial, this trivial sheet. And which are the fixed? If I choose a matrix of this form, then what I'm gonna get? I'm gonna get sheaves which are direct sums of two sheets of small rank. And then, of course, if I can pick decomposition into more W's, will have a bigger thing too. And it's actually very convenient from this to introduce M of W, which is disjoint union over all E and dW, and then the formula becomes, of course, that M W prime plus W double prime is the product of M W prime and W. Which is also geometrical. It's very natural to once you to fix rank and take the union over all C2s. So now so that will say that the general theory of the stable envelope will give us a map, or will give us a stable envelope, will give us will give us a map from a product of Nakajima variety to a Nakajima variety where you take the union of this vector. So it's this map that we will study. So here, if we look at this picture, there are very kind of elementary geometric point here is these are different components of a C-star acting on some variety, and these are different connected components. And different connected components of a thing X log is always ordered by what lies in the closure of itself. So if you recall, so if fi, if I take my x log of a, this is disjoint union subcomponent fi, then the set fi is partially ordered. By the direction of the flow. I.e., you would say that fi is bigger than fj if I take the attracting manifold, and all my attracting manifolds will be with respect to z going to 0. And so attracting manifold of fi, the closure of it intersects at 2. And so how are these things ordered? And so there's a very simple computation, which I'm sure all of you know how to do, but just to make sometimes I think it's okay sometimes to explain elementary things in lectures. So suppose I have on my Nakajima variety by construction I have an ample bundle. By construction, the line bundle, if I take the following thing, if I take the product of the determinants of the spaces Vi descend to vector spaces Vi on the pre-quotient descend to vector bundles on the quotient. So the determinant of this to the power C Vi is ample on M L. So if I have if I have some fixed point equal P1, and I have some other fixed point P2, and suppose this lies in the closure, this lies in the closure of something attracting to P1. So then that means there is a C star orbit here. That goes, so this is C star orbit, the closure of which hits P1 and P2. These are fixed points. This fixed point sits in F1, and this is in F2. So this is different. So this is, then what's the degree of my line bundle restricted to this orbit? It's a positive number since it's an ample bundle. This number is positive. And this is then, by localization, what is it? It's the weight, you take the weight of L at P1 minus the weight of L at P2 and it's divided by the tangent. The weight is the weight of the tangent space at P1 to the orbit. And since this is at P1 is directions attracting, this number is positive. And so therefore the numerator is positive. And so what is then so what is this weight? If I restrict this weight to some so this is I act on this space I act with if I have my z acting like this, then with my z acts by this is the z eigenspace and this is the one eigenspace. And so when I take the when I take this weight here is z to the sum of theta i's times w d i's prime. This is a space. If I act by z on vi, then the determinant gets z to the power dimension, which is little vi, and then I raise it to the power theta, so I get this. And so this components therefore are ordered by just the dot product of theta dot. In particular, the largest one is when all v goes here. Well, no, I mean, suppose usually, so well, let's use, for example, we'll take theta to be just positive. All components with theta positive. And the other ones can be also somehow dealt with very similar, but suppose they're all positive, then the largest one is when all v goes on this side, and the smallest one is when all v goes on this side. If you were ever confused in like Serre's construction, which way the torsion goes, you can rethink this example from that point of view. So this would be so now I'll recall what was since the definition of the definition of stable envelopes was a while ago. Let's refresh ourselves. So what's a stable envelope? So I operate now in this example. So this is my C star action, my fixed laws are product of Nakajima varieties, and so I do stable envelopes in this example. So stable envelope. What this is a cycle, it's Lagrangian cycle in the product of the target, so which is, maybe I'll just write W, so W cross and so it's a cycle, Lagrangian cycle. Which satisfies the following three conditions. First condition is that near that, so inside here, this is embedded in here, and so you can ask that this product is embedded here as a fixed point set. It's a locus of direct sums. The product of Nakajima varieties are embedded here as a direct sum. And so you can talk about the diagonal. So near diagonal, is the attracting the correspondence the attracting manifold. And what does attracting manifold mean? Attracting manifold means that these are direct sums of co-representations, and these are general co-representations. What this means is general co-representation is attracted to this one under my action. It just means it has a sub isomorphic to one and the quotient isomorphic to the other. And so this attracting manifold, this is just the locus of extension. So this is just extensions, the locus of extensions. So where you have the sub is the extensions is the other. You always think next to somehow go big. So these W's are primes are the quotients, and the W primes are the sub. So this local curve representation, there are extensions this way, so I'm locus here, and under the action that rescales this by z, that this extension will split eventually. And then the second condition, then if we restrict stop to other components of the diagonal, so this means we restrict stop to a product which is where I now have to write down, so there was a product where, stop writing here, there was MB prime W cross M W prime. W prime, and then there's some V3 W prime cross and V4 W double prime. And so then this is now not equal to 0. And we're restricted to this locus, then the degree of this in U, which is the U is an element in the Lie algebra of my where Z is exponential of U. So U is the Lie algebra of the group. The degree of this is less than 1 particle dimension. So then this gives us a map from the product to, so this is applying this cycle as a map from the cohomology of this side to the cohomology of this side to get the map. And so then the R matrix the R matrix, R of U, although it depends on all possible, so I wrote it R of U, but in principle that depends also depends. And it's an operator very homologous. It depends on everything. The only reason why you single out dependence on U is because this will be an operator in the homology of the fixed locus. So U, X, they're trivial, and so this depends on somehow. U is just a variable, so it has no geometric significance there. And so this is then, so you take the stop, and stop as Z goes to 0, and then you compose it with the inverse of the map stop as Z goes to infinity. This is also known as unstop. And so then this is a map. So this is a map from equivariant cohomology, inequivariant cohomology of the fixed locus. So this is cohomology here, and then whatever group I have left, of the product. So I'll just write. So it's by Coulomb is the same as the product. There's a prime here. And the main claim about it, what's the main claim, is that this satisfies. So it's an operator in the tensor product of two things. And then so it has a potential to satisfy Yang-Baxter equation, which is the spoken at length at what a Marvel's equation is and how it's so this satisfies Yang-Baxter equation. We call what the equation says. The equation says that if I take a tensor product of three things, and I take R12 just with U1 minus U2. This means it acts in the first and the second factor, R13, U1 minus U3. are Z3, Z2, E. So this is going to be the other way around. So this is not going to write that. So how do we see this? Well, it's actually easier to see some. Actually have maybe the way to think about it is like this. So consider, so if I have a, so what's the, how we going to see this? Well, we take our torus. So if I take our torus A to be now the isomorphic to C square, and this would be acting in my space W. So this will be going to the product of GL WIs, and the way it's going to go is that you'll have some variable, and then Z, so many ones, so many Z's, so many W's, and so many ones. Maybe W was not the best choice of the variables, but W, many W's. Here, but not really. And so, which are they? So the Lie algebra of this is a two-dimensional. Maybe how about we'll call it that one that does that. And then of course this is modular scalable scaling, so it's more like a maximal torus in KGL. And so what's the Lie algebra looks like that? And consider, so if I have a Lie algebra element here, I consider the following sort of, I don't know, like a constructible function of psi. Namely, over psi, associated with psi, I will take psi. I will take the equivariant cohomology of x psi. Like over the origin, I have the whole space. So here I have the whole space sitting. Then whenever the two of these eigenvalues coincide, so then over the, whenever the two eigenvalues coincide, so this was Z I over J, get here and get the product of two Nakajima varieties. Here in the product of two. And then generically I get a product of three. Generically, this is a product of three. And prime cross and double prime cross and true. And this, of course, this picture you can draw in higher dimensions too. And so then associated every facet of every chamber in this cone, I have a map from the I don't know. This is for general torus action on the genuine variety X. So suppose now I have some chamber and a facet of it. So chamber. So we have not a chamber. I have a facet of some dimension and a facet of not a facet of what's it called? Cell. What are they? What in the polydopes, what are the vertices, the edges, and the facets, what they call? Cells, right?
The face.
Face. Faces. Okay, I have a face of some dimension, and I have some I don't know, the adjacency between two faces of two different dimensions. Then I can consider a map from the so here then here I have a cone here. This sits in some this whole thing sits inside some Lie algebra called A1, and this spans some other Lie algebra called A2. And so here we have a special, sort of like a specialization now, which is this stable envelope in the torus, which is the quotient of the two, and corresponding to the cone, which is this cone. And then the statement that these maps are compatible, meaning if I have here, if I have generic point psi, and I first go and I can either take the stable envelope all the way here, or I can first go to a facet and then go within the facet. First go to a wall. So well, let's forget the general discussion. Here we have 6 chambers, 6 walls, and a point in the middle. And the stable envelopes I draw, they all correspond to the origin being adjacent to the chambers. But I can also have the walls adjacent to the chamber, so I can first go on the wall and go here. And the statement that, of course, is commute. And the reason they commute is because if I take the composition of the two, it's pretty clear that I'm going to get a cycle that satisfies this condition. And this condition says that if I multiply two matrices with some kind of small off-diagonal elements, I get a matrix with small off-diagonal elements. This compatibility is actually the key why we have to use this fancy stable envelopes and not somehow actual attracting varieties, because for actual attracting varieties it will fit. And so then if you look at this diagram, you'll see that both sides here, these two sides, what they tell you is that if you want to go from generic point here to the generic point in the opposite chamber, the stop up, and then you're going to do the inverse of stop and get here. Well, this you can do by crossing this 3 walls or this 3 walls. And that's precisely what this equality tells you. Because when you here in this picture, it's either maybe here Z1 becoming equal to Z2, and here Z2 becoming equal to Z3 first. And so that's the first wall you cross in one side, and then the first wall you cross on the other side. And then you cross the Z1 equals Z3 wall. You almost cross that wall second, and then you cross the other wall, and you end up here. So that's and so, I don't know if you have fresh it in your memory, but we'll spoke at length that once you get a solution of Yang-Baxter equation, you get representation of a certain topology. I wouldn't say exactly for free, we would have to work to get the solution of the Yang-Baxter equation. But so if I take this tells me that I get an action of a certain Yangian And the way it's done is you choose, and the way it's done is you take namely what you take an auxiliary Nakajima variety. You take this R-matrix acting here, and you take its matrix elements, take matrix elements. In the auxiliary space. So then you get some operators depending on you here, and then and the coefficients. Of the 1 over 2 expansion. If you get an operator here, you pick some universal thing acting in a tensor product, you take some matrix, whatever matrix element you want to pick here, and then you also pick some coefficient of u. And so then our goal is, so then again by general principles, this would be some half algebra. And our goal, which will act on Nakajima varieties, is our goal to understand this. So this is somehow, this is slightly, the logic here is usually a little bit reversed from what usual logic when you first define an algebra, then construct a representation. Here you first have a representation and then you study what is the algebra you get. So there are two kinds of things here. So this Yangian, so by anticipating further development, this Yangian would be a deformation of topological deformation. Universal development of some Lie algebra tensor polynomials is not variable. And inside here, there are two, we discussed this in an example of SL2. So somehow SL2 corresponds to this is like a cotangent space of the graph main is Nakajima variety associated to the curve with one vertex and no edges. And so then this is an example we already discussed it in certain amount of detail. And so we already saw this here somehow. So this will now experience it in generality. So inside here we have two sorts of things. Inside here we have of course the Lie algebra itself. Inside here there's Lie algebra. We'll talk about it a little in a second. And also we have polynomials valid in the Cartan. So this is both have nice property. One is commutative algebra, the other is Lie algebra. One is so both remain. Both remain in some sense undeformed. It's the commutative relation between them that gets deformed. So that this stays a commutative algebra, and that stays the same Lie algebra. And so what these guys are, these are the vacuum matrix elements. Namely, in this product, when you act, so here we can take, any, so the distribution of the vector v, these guys somehow distribute these two things, and then the simplest thing is then v gets nothing on this side. V is just 0. So that matrix elements is, we'll say v prime is 0. And so then this thing is then space, this space are then points. So when Nakajima varieties, when they, so dimension of 0, the value is 1 point. 0. And so then we can somehow, these are very special matrix elements here, and this is very somehow, again, for simplicity, we can assume that P is positive. In general discussion, it can also be done slightly. Notation gets more complex. And then this, so we'll talk about first this vacuum matrix elements for a second, before we begin talking about them. And then these are recovered. How are these recovered? These are recovered as 1 over U coefficients of the R matrix. This R matrix, this has the property that this has the property that starts, this is 1 plus O capital of 1 over U. And so it's 1 over U. At infinity, this matrix is 1. It's constructed so that it's 1 at infinity. And so then the first non-trivial coefficients you can pick, those matrix coefficients give you this action of this Lie algebra G. So we'll talk about them next, after we deal with this. What are these vacuums? So, again, so we'll just for the sake of discussions, I would have this. And let's say E prime C. Inside here, I have embedded M0, B, and 0. W prime cross M. And this is just a point. And what's so special about this component, remember when we talked about the ordering of a fixed component, this is the one where all the V gets on this side. This is the smallest. This is the smallest. So there's nothing. There's in other words, it's saying, okay, there's somehow nothing. It flows. Everything flows into nothing. This flows to nothing. And so if I now consider, so that's if I now look at this composition, what's it going to look like? So if I can write this composition in two steps. I can consider this stable envelope, and then restrict it to these points, and then I take the inverse of the same. Followed by restriction. This is just for pedagogical reasons. I want to talk about matrices. Pedagogical reasons. This is not. So what is this matrix going to look like? So this matrix is going to look like this. So this will have some block triangular form. This corresponds to my fixed component, and this is my vacuum component here. This is the smallest one. There's some stuff here, and there's 0 here. What's on the diagonal? On the diagonal, we have to take the attracting manifold and restrict it, and restrict back to the fixed locus. So when you take the attracting manifold, restrict back to the fixed locus, you get the Euler class of the normal bundle to attracting manifold. And so it's the Euler class here. What stands? The general stands in the squares here. This is what stands here. Is the Euler class of the unstable part of the normal bundle. And then what does this matrix look like? Well, this is going to look the same thing, except now I'm going to go the other way. And now what stands here is the Euler class of the stable, of the attracting part. Strictly speaking, when you actually define stable envelope, there's some orientation issues. So there's plus minus. I'm not going to build too much of that. Now, if I now the inverse of okay, so if now we teach our students in the algebra how to multiply matrices, and so point about this product of matrices is that this matrix element of the product will be just the product of these two. And so in the vacuum matrix element of the R-matrix, therefore, so if I take the R-matrix and I take it to the vacuum, so on my auxiliary space, I take the vacuum matrix element, and in my so this is going to be, what's it going to be? It's going to be, well, it's the Euler class, it's some plus minus, the Euler class of the unstable part of the normal bundle, divided by the Euler class of the stable part of the normal bundle. With the symplectic form, so what do we have? We have a symplectic form, which tells us that m plus times n minus times the weight, the space of the weight of the symplectic form. This goes to trivial representation. This is h bar is the weight of the symplectic form. And so then, with this all these plus minuses, the thing exactly arranged so that in the end you get the Euler class of n minus divided by the Euler class of n minus twisted by a character, which I just write it down. And so what this thing is? This is the great Euler class. And so n minus, on my torus, my construction, that my torus was acting with weight z on n plus, and therefore 1 over, so somehow the weight of this space is z inverse. And so this equivariant Euler class will have the form, the product, or in the numerator, so the product of the following thing, to take u minus xi over u minus xi minus h bar. These are the short roots. And so then I can write it like this. This is the exponential of this sum of logs, right? So the summation of k, I take log of this, and log of this will come to be 1 over k k x bar plus h bar k minus k. So point is that this is through sum of churns. So this first you can expand to get sum of churns to the power k, so you get some expression in terms of churn character, U bundle. And the point is that this will generate this matrix element as elements of U will generate for you all possible characteristic classes of n minus. So this will start as 1 plus the rank of n minus over U, them is divisible by h bar. So h bar over u times the rank of n minus plus h bar over u squared. And here will be c1 of n minus plus some terms with h bar, which is have to do with the rank. And so, anyway, somehow, if you look at the u to the coefficient of 1 over u to the k, this will always have h bar in it, and then the next coefficient will be the Chern k minus 1 of the n minus. And so what's n minus? N minus, well, it's not, oh, sorry, it's just exactly what I wanted here to use. So I have my this was inside here, and there's using m 0 w1. What's the normal bundle to this in here? Here we already have a curve representation. All you do is just a trivial framing speed. And so the normal bundle here will be just the home. So the normal bundle is n minus. N minus is just direct sums of homes from this w prime I to the I. And then n plus the other way. So n plus. N plus is this. Whatever in mind, look at that. Yeah, sorry, not the good notation, the other way. My torus. And so, remember, the torus was acting here. My torus is acting here with weight z and here with weight 1. So on this guy is going to act with weight 13. This is act on here with z. So which is why it's 1. So conclusion is that this vacuum matrix elements, this generates the algebra. So this equal. So the conclusion is this is equal to the algebra generated by characteristic cup product by characteristic classes. Of these topological bundles. So, embarrassingly, it's apparently unknown whether the cohomology of Nakajima varieties is actually spanned by both. So, these apparently, so I mean, my understanding from the experts is that what you have is you have a resolution of diagonal by these bundles, and so, but you don't have a. So you think you're done, but since the variety is not proper, then it's not. I mean, somehow they cannot finish the argument. However, what can be shown is that anything that commutes with it is so that the cohomology is the commutant of it. So this could be a maximal commutative subalgebra. This, we don't like that it's a maximal commutative subalgebra of the Yangian, but in principle you could. I mean, in principle they sum up working. So I'm saying somehow. I certainly expect that this is an entire cohomology. And Berthik is not even known for H2. This is, so, I don't think it's a hard problem, but I don't think anybody worked on it. So what I was going to say about it. So
So in particular here, these two things have an intersection. The intersection between polynomials in Cartan and the Lie algebra is Cartan itself. And Cartan subalgebra acts by 1 over u coefficients here is this. And the ranks of the topological bundles, they just quite precisely the VI. Right? So in other words, this decomposition of the cohomology, in other words, when we take the cohomology of MW, and this is of course, this is disjoint union, this is of course direct sum of the cohomologies of MVW. Now this decomposition V, this is decomposition, this is a weight decomposition. Decomposition for this Cartan subalgebra. Because what does, if you know all the ranks of these things, that is precisely known to these Right, so I don't know, maybe I don't want to start the discussion of Lie algebra today. I'll just finish by saying that this is I'll check whether there's something in my notes that I wanted to say. Yeah, so maybe I'll just finish by saying that what we will somehow set out to prove. What we set out to prove, maybe I'll erase this with the class computation, is we were set out to prove that if I take so if I get some elements of if H is in my Cartan subalgebra, and I consider trace of over the auxiliary space. So I take M W prime. So this is homology of W. I'll take Q to the H acting in the first factor under 1 times this R-matrix of W Q. So this will be now acting in the cohomology of my original Nakajima varieties. And so what our goal is to show that these are the operators, these are operators. This commute by general principles of the Yang-Wax equation, these are operators. Of quantum product this is a ring and there's a quantum product in it, and so you use operator of quantum product. And so what we just checked is that this works for Q equals 0. Because if Q equals 0, so we didn't just check. This is not how I spell just check. Q equals 0, because what's going to happen in Q equals 0? Q equals 0, the Q was waiting. Q was the parameter was counting curves. So if you take Q equals 0, do no corrections from no curve corrections to the cup product. So then the quantum product at so this has a parameter Q, and this stars at 0 is just the ordinary cup product. And so then on the other hand, this if Q is 0, this is a projector. So this acts by Q to the this in my space there. This acts by Q to the V. And if I set Q to 0, then it's projector on the vacuum subspace. And so indeed we check that the project somehow works out. And However, if you so one thing you're thinking of sometimes, which is that you don't think why it's too easy, it's here not only that we check that these are operators of quantum product of classical products, we in fact specifically said the product by what? So this characteristic class that I just erased, that's what it acts upon. Whereas in the quantum case, we won't be able to say this actually. So you'll it's a quantum product by something which is itself Q dependent. So then to say you want an actual quantum product by some geometrical meaningful operator such as this, then you'll have to have those lie the same algebra, which you have to work harder to get. Well, anyway, I think probably it's too late in the day to start a discussion of the other part of the Yangian, and we'll just stop here for today.
Questions?
So this is quantum product, just zero.
Gen 0, yeah.
Can I just ask in general?
But say if you do genus 0, so if you take like genus 0 stuff in the modular of shapes, you in fact counting higher genus stuff on the threefold. So you take the interpreted this think about the way to think about Nakajima variety. Nakajima variety is like modular of shifts on some non-existing surface. I give you some Cartan matrix declared to be like the pairing in cohomology of some non-existing surface, and then I construct some variety which is sort of like modular of shifts on that. And so then the study of genus, you can take the study of genus 0 or any fixed complex structure curve in that corresponds to sort of studying like all genera on the threefold. I mean, think about when you have a curve in the Hilbert scheme of point, then it's going to be some it's going to be some higher genus curve in if you have a threefold fiber and surfaces over some curve, and I consider a curve in the Hilbert scheme of point, then of course there's going to be some higher genus algebra in threefold. I apologize.
So on one side, we have some integral hat, and so presumably the KGB and the KP will fit into that context.
Maybe, I don't know, in some, yeah, I'm not sure exactly. In some sense, maybe, yeah. You have to go, you have somehow degenerate very, somehow a lot of the generation has to be taken. I'm not sure exactly how to go to this down. Yeah, well, sorry, I apologize. Maybe you should finish your question.
No, I just assumed that one can see these integral hierarchies within this context, and then they record the solutions to them are given by the full ground representation that has all genus.
Yes, but so what would be the point for this? Somehow you have to somehow specialize from threefold theory down to, if you want to say something like KP, like you probably want to go down to one-dimensional things. It probably can be done, right? I mean, so this has to do with like full-grown Witten or full-down-Thomas theories of threefold. And then this more classical integral hierarchies you find if you study this new problem for not so threefold study, just curves, which isn't the point. And so that means from whatever structure you see in threefolds, you have to somehow find some way in which they some corner, some very specific corner in that thing. But that's certainly in some sense geometrical. That's certainly informational there in terms of how to just repackage this. So this would be, so at the end, so when we would be all done, there will be description, of there will be description of in some sense the entire, let's say certainly of all toric threefolds, but in some sense in all threefolds of all curve counts there in terms of representation theory of GL of Yangians of some finally on how to actually somehow to unravel that structure and go back to the integral hierarchies you mentioned that I haven't investigated. And the structure is certainly genetically contained, but if you can somehow effectively specialize, that maybe. I haven't thought of it. Maybe next time, or by next time I'll think of it.
Because the Roland became a few weeks ago in the talking physics, anyhow, one can see KP and KP from a representation of the output. Because here also we have some representations. Well, we have the big diagrams.
Yeah, but this is somehow next level. These are, so in his stuff you said actually find the algebra. And here you study like Yangians of a finely algebra. Means this is like, twice the number, it's like double loops into it. So if a final algebra is like loops into some finite dimensional algebra, these are like loops into loops into. So it's a lot richer structure. So how to exactly somehow correctly take specialization there, that I'm not sure. It must be possible somehow, but it's just not prepared to answer this question.
Other question? Thank you.